Okay, so in this lecture, we will be covering nested quantifiers. So last time we spoke about the universal quantifier and the existential quantifier, right? It was just ways of describing the possible truth value of a sequence of predicates over some domain, right? Well, you can nest quantifiers now. So for example, let's consider this one. So okay, so this would be a nested sequence of quantifiers. So how would you read this? This would read for all x, and let's just for now assume that we're dealing with real numbers. So I'll just go ahead and say at the outset, domain of interest, real numbers. Okay. So for all x, technically it'd be for all real numbers x, but for all x, there exists y such that x plus y is equal to 0. Okay. If now, is this a true statement or not? Yeah, right, like the additive inverse of a number. So just take x to be equal to, take y to be equal to negative x. Okay, so this, like intuitively, just like reading it out loud, we can like suggest that this is true, right? So what about this statement? There exists x for all y such that x plus y is equal to 0. So let's just read it out loud again. There exists x so that for all y, x plus y is equal to 0. That's not true, right? So this is an important point. The order matters. Okay.
What if we move the y to the front?
There exists x for all, there exists y for all x. It should be the same thing. And it doesn't matter what variable you put here. What matters is the quantification. So, and some of the times it can be actually confusing when you're trying to read it out and figure it out. It helps to like actually write it out sometimes. Now, like if you were confused on this one, right? What exactly is that saying? Well, it's like there exists x such that, right? So let's just take, let's just write it out. Like let's use integers just because it's easier than real numbers to write out. But so there exists x, which is an element of the integers. I'm changing it up. So for all y, make sure that we know where it comes from, such that x plus y. So what's another way of writing this? Well, this is logically equivalent to there exists an integer x. So for all y that are integers, we have this statement, right? So before we choose x, we have like x plus 0. I'm going to be careful how I write this. Is equal to 0. Okay. So we're taking every possible integer, and it's over this universal quantifier. So the universal quantifier is and, right? So then we haven't considered x yet. We're just enumerating out all the integers. So what's another one? What's another one? What's another one? So that's like a single variable predicate, right? So this string goes on for all of the integers. And just ask yourself, is there any one x that satisfies this? Okay. And if you wrote it out completely, like as soon as you pick one x, you'll see that it's false, right? So like, it's going to be a mess to write this to illustrate the point. So this is like the or over all of the things in there, right? So it's like, yeah, it's going to be a mess for me to write. I'm going to do it anyhow. So I picked one, let's start at 0. And 0 plus 1 is equal to 0. And 0 plus minus 1 is equal to 0. And dot, dot, dot. And then do it again for the next integer. But now we have an or. Right? And now the or is going to, so the next integer will be like 1 plus 0 is equal to 0. And 1 plus 1 is equal to 0. And da 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 da. And then another or. Right? And that's going to be false. That's going to be false. Or that's every single one is going to be false. So then we see that like indeed it's the case that this one is false. Okay. More or less get the idea. All right. So let's try to look at maybe a more complicated one. All right, so draw, say, x, draw y. I'm gonna pick a good one. X greater than 0 and y less than 0 implies x times y less than 0. Okay, so take a moment to think about what, when you look at that, it would be nice if you could just, in your head, read what it means, or what it says. And then after you know that, you can figure out what the truth value is. So for all x and for all y, if x is greater than 0 and y is less than 0, then x times y is less than 0.
True.
It's true. It's just saying that a positive and negative product is less than 0 if x and y are both non-zero. Yeah, it's true. Okay. It's not too bad of a concept, right? But what about if we negate this thing? What does it become? Because remember, once you apply a quantifier to predicates, you have just a normal proposition. So we can negate this thing and get something. What does the negation say? right? So if we negate it, so through negation, we know that this one's true. Whatever the statement we get, gotta be false, okay? So just for fun, I suppose, if we negate this statement, all my blacks are running out. I guess all I did was put a negation sign. That doesn't tell me anything. Because we would like to understand what words with the negation is saying. Right? Like more so than just saying it is not the case that for all x and for all y that. Like, let's like break it down some more. So what happens when we take the negation of the universal quantifier? Morgan's law, but we more or less figured something out last time, right? Right. It becomes the existential of the negation, right? So we can just write that out. There exists x, and then negate whatever follows it, right? Whatever proposition that is. It better be false. So there exists x, and then it's like even harder to say. It is not the, there exists x, and it is not, I can't even like say it, not the case that, right? But we know something about negating the universal. The negation of the universal becomes the existential, right? So better be false, because we know the original one is true. So now this is a little bit easier to say. There exists x and there exists y, such that it is not the case that x greater than 0 and y less than 0 implies x times y is less than 0. Yeah.
How come the and still remain not switched to or?
I haven't sent it in at all, right? Like, it is the negation of all of this stuff. There hasn't been any, it hasn't encountered any of the logical operators that we know. Yeah, it's still on the outside. But we don't really know how to negate the conditional. But we should know what what the negation of the conditional is. We definitely should know that.
It's the negative or the negation of the hypothesis and or the conclusion.
You're close. It's the hypothesis and not the conclusion.
Oh, no.
I remember I tried to emphasize that one logical equivalence, that like I emphasized that the negation of if P and Q is P and not Q. Remember that?
Yeah.
So we can apply that here. It's a mathematical statement, but it's really just proposition, right? It's just like we have a hypothesis and a conclusion. So I know that the negation of this is going to be not, so this and not that. Right? That's your hypothesis, all of that. And the conclusion is here. So what we get there exists X, there exists Y, such that X greater than 0 and Y less than 0, and not that, right? That's and not that, not the conclusion. Okay, so maybe it's becoming a little bit easier to read. So what does this say? It says there exists X and there exists Y, such that X is greater than 0 and Y is less than 0. And well, it is not the case. So what's the negation of this statement? That's the opposite of that.
Like greater than you,
What?
greater than you.
Almost. Greater than or equal to, right? Because it can't equal that, so the opposite has to have that possibility, right? So again, there exists X, there exists Y, such that X greater than 0 and Y less than 0, and X times Y is greater than or equal to. So that's the full negation. So now, well, I already said it. There exists X and there exists Y such that X is greater than 0, Y is less than 0, and X times Y is greater than 0. That's false. So yeah, it's verified, but having the ability to do this gives you a lot of flexibility in how you look at logical statements, right? Like, if you have, and this is math, right here, these are like math operations, but realistically, this applies to any time there's conditional statements. There is this, so I've been teaching discrete math for a very long time now. Like pretty much every semester since I've been in a lecturing type position, I've taught 2-3 courses of discrete math. And at Texas State University, I ran into one of my old students that took my class at a coffee shop, and he was studying to go to law school. Like he was trying to like take the entrance exam or something. And I was just curious, so I looked at it, and you'd be amazed how far through that exam I could have like been okay, just based off of knowing propositional logic.
Wow.
Yeah, so this is probably a reason why law schools are happy when math majors apply. Because the majority of formal reasoning is in the terms of like conditional statements.
I think there's like a statistic that says like people who study law or criminal justice have a lower chance of acceptance than people who are engineers in law school.
Yeah, and this is, a part of it is this, it's just this, it's like logic. It's the foundation of formal reasoning. So having the ability to take statements and break them into variables and then look at what the negation is and understanding what the negation says is actually kind of important. It helps you understand the original question, the original statement more. If you know the statement and its opposite fully, then you understand the problem at hand, which the problem is typically determining if the statement or its opposite is true or false. Right? In fact, I encourage all of you to really like go look up like law entrance exam like examples and like see like you'll like literally like in the first few pages you'll probably start seeing something involving logic. Okay, so ooh, this looks kind of fun. Yeah, let's try to figure this out. I don't think I've done this example. I've done most examples in Rosen, and I just came across one that looks interesting. I don't think that. If you can't tell, Rosen is like my favorite discrete math book. I think it's like most people's favorite discrete math book. It's just too expensive. Okay. All right, so let's say we're gonna pretend like getting ready to take a law of discrete. So f of xy is x and y are friends. I know y'all can see it, but I'm afraid that my recording is not going to be able to pick up these. There. Okay. All right, so this is there's two variables in this predicate, right? So this propositional function, which I'll just call from now on that, because I think it's more descriptive. And it says we need to translate this statement. So I'm not going to read it out, I'm going to write it, and then we're going to look at it. Oh, one more. We're gonna have a room that implies okay. So for all x, for all y, I mean, no, there exists x for all y and for all z, such that if f of xy and f of xz and y not equal to z, then it is not the case that f of yz. Well, we have to translate it. What does it mean? Basically, what we've done is we have a propositional function, and we have something, we don't know what that something is, that is described in terms of that function. We have a conditional statement, right? So, can someone tell me what this means?
X is shows y and z, or y not z.
Don't forget the arrow.
And
Y create a conditional.
So what's the Z? Is it friends, like a friendship? Signify the friendship?
So what is the domain of interest here? It looks like it's going to be just people, right?
Yeah, okay.
So any more guesses?
It's a mixture from. What's the Y, what's the symbol for the Y and Z? Not Z. You haven't seen that.
Y not equal to Z.
Y not equal to?
Yeah.
Oh, it's usually equal across.
Y'all can guess it. Break it into its components. So
So we know.
X and Y are friends. So okay.
So they're not friends.
So you can't forget the quantifiers here, right? There, let's just say student. Let's say that we're students, right? So the domain of interest is students. So there exists a student X for every student Y, for every student Z. Okay? That's a good way to start. Let's say it out loud. There exists a student X for every student Y and every student Z, such that X is friends with Y, X is friends with Z, and Y is not Z, implies Y and Z are not friends. Right? And we don't know the truth value of this, right? But we can translate it, right? So
It would be true.
I should probably, well, let's see. I don't think we will be able to determine the truth value of it. We might after we write it out, right? So let's write it out. So there is a student okay. I want to write it out the best I can. I kind of don't want to use X, but I kind of just want to say there is a student who is friends with Y, who's friends with Z, and right. So what is this saying? If Y is not Z, so that means that
They can't be the same person.
right, they're not the, so basically what this whole thing is saying is that this student is friends with two different students, right? That's what it's saying, like, this student X is friends with every student Y, every student Z with these different, so sounds like there's like a really popular person, right? It's like, so there is a student who, no. There's a conditional statement there. So there is a student so that if this student is friends with two other students, I'm kind of assuming they're different, right? So that if this student is friends with two, oh, maybe I should say it a little bit better. So that if two students are friends with this student, or two others, so yeah, if two students are friends with this one, right? That kind of like implies that they're different and they're both friends, right? So if two students are friends with this one, so if that happens, then these are not friends, so they're not friends. So if we write it out, so there is a student, so that if this student is friends with two others, oh no, we should say, so that if two students are friends with this one, that's what we should say. I'm trying to write out the best. I could write out very long. I'm trying to do it the best the first time around. So we're gonna say there is a student, so that every pair, it's not gonna, that's gonna be too formal if I say every pair of students that know the student.
So like Y and Z are like two schools, and X is like a teacher or something. So X is.
Well, like the schools couldn't be friends, right?
Well, yeah, but the teacher can have a great relationship with all
Company just
Ys.
name the two.
I almost have to introduce the variables, but I don't want to.
The company just put it in for X, like Josh or.
Because we don't know who that student is. Dude, I knew this was gonna be kind of fun,
It's an
right?
existential.
And so there is a student, so that any pair of students who are friends with this one, I'm gonna say pair like means like there's, right, so that any, so. Oh, no, I can get rid of that, I'm overcomplicated, I just have to say, there is a student, so that any two friends of his.
Can be a common,
Are gonna be enemies? That's crazy.
can't say common, uncommon.
Oh, that's what it's saying, it's so that, that's what it's saying, it's so that there is a student so that every friend of this student is not friends with another friend.
Yeah.
That's what it's like, we're distilling it down now, right? We're getting back to where this thing came from.
Wouldn't it be friends amongst
So
themselves?
student and
Does that mean Y
friends
zero
are not
shows the other?
friends.
So all every Y.
Yeah, and then every single one of them, every pair of students that you put with this person that are friends with them are not friends themselves.
Okay, yeah.
That's what
If
it's
they
saying.
are friends, then
Yeah,
it
no.
would be false.
UT.
Right, yeah, so if they are friends, so they'd be false.
Or if they were the same person, that would be false.
So I would say in general that this is probably,
There is a student whose friends are not.
yeah, this seems true. Like, are any of your friends with any, like,
Can we do like A and M students and UT students? Like, does that work? You know, like.
right, like,
Yeah, that round.
it's like saying, like, well, no, but if we think about it, right, like, we have to, like, I'm trying to get y'all to like talk about it as much as you can, but like, let's like nail it down right now. So, remember how I said it can be confusing when you start like, trying, like, let's just think. So, this is saying something, and, so Y and this C, Y and the next C, Y, so, and then the next Y, next C, so it's like, this is really like saying every possible pair of students. Okay, so let's just put it on you. You are the existence. So like let's test for you if this can possibly be true. So you, okay? So for every pair of students, that if they are both your friends, then they are not friends. Did that distill it enough for you now?
But we still have to account for the fact that they're not the same person with that second, with the.
Oh, yeah.
The one. So how would you?
So what if you,
translate that?
okay, what about this? I can like nail down a given instance. What if you don't have any friends at, like, any friends that are students, right?
Yeah, no friends, bro.
So like, what if you have, so let's just make students this room to make life easier on us, right? So what if, like, every single one of you, what if you didn't have more than one friend? Would this be true or false? Every single one of you did not have more than one other friend that was also a student.
False.
Why? Why do you say false?
Because they have to be friends with both Y and Z.
Which means this is false here.
Oh, I see what you mean.
So what does that mean the whole statement will be? No, true. Anytime you have a false hypothesis, you have a vacuously true statement. Remember how I tried to emphasize that?
Yeah.
So if
I see.
none of you have,
Oh, I see.
so basically like, if none of you have more than more than one friend in this classroom, and that's our domain of interest. If none of you, this will never be satisfied, so this statement on this classroom would be true.
Right.
Okay. Now, I'm assuming like there's at least one person in here. Like now let's go to the whole school, right? Now, in here, let's look for existence. So I'm assuming one of you has two friends that go to the school. Maybe not. I've got one over here, right? You. So you have, so there's a possibility of this being true for you. So we have to like think about this now. So pick any pair of friends that you have at this school, right?
It's just.
There's just two, okay, this is good. That makes life simple. So you pick those two friends, okay? You're friends with both of them and they're not the same person. Okay, let's check the hypothesis. Now we have to go in and check. Like this really emphasizes like how the definition of conditional works, right? Because most of you is never true, but the whole statement is just vacuously true. We don't have to ever check anything. But for you, we do, right? Now, are those two friends? Friends. Ah, I mean, so this is false, right?
In that case, or does
Yeah.
it matter how we know that?
Well,
You wouldn't know that.
whoa. There exists a student, and you have two friends, and they are not, and they are friends, which means the negation of that is false. So your hypothesis is true, and then this conclusion is false.
So it's false.
It's, this whole thing is false on students at UHD because of that one existence,
Right.
right? That one existence, you made this statement false to the school. It's like, it's kind of fun breaking these things down because you can take ordinary statements and you can really just like, oh, actually, let's figure out what the negation of this is. Because you made this thing false, so the negation better be true. What does the negation say? Let's find out.
Before we move on, the problem is the condition, right?
Yeah, it's like there's an arrow pointing here. So because his friends satisfy this, and because they are friends, if you negate that, you have false.
So when we negate it, that means that will become wrong.
Well, no, it's just like, no, just this thing.
Oh.
It's like not, what are your friends' names so I can use them as an example? Ronnie and Fonzo. So Ronnie and Fonzo are friends, right? So Ronnie and Fonzo are your friends. So if they are if Ronnie and Fonzo are your friends, then they are not friends. Right? That's false. Y'all starting to get it now?
Yes.
Now let's see if we can figure out what the negation of this is, because that better be true on students at PhD. Right? We know how logic works, even though it might not make sense right now, but let's find out. Hopefully so Ronnie and Fonzo are friends, right? I have to emphasize this one more time. So if Ronnie and Fonzo are friends with you, which they are, you go in here, then they are not friends. Oh, it's a false statement. All right, so now we need to negate it and see what this means.
Question, have we omitted Y, Z? So that-
We've omitted because like if they just
Where we omitted it, right?
more or less like, well, no, we haven't really omitted it because this statement here with that says that that friend is Ronnie and that one is not Ronnie.
Yeah, okay.
Right, so, right, it is not the case, X, draw Y, draw Z. I think I left out. Yeah. That implies
Last section should be Y.
X, Y, X, Z, Y, Z, yeah. Then. Okay, so. This is false, the negation better be true. So we know what's gonna happen when we send the negation in, right? Like that becomes universal, that becomes existential, that becomes existential, and then we negate that whole thing. So. Universal. Existential. Existential. And then we know the negation of the conditional. We should remember that now, right? The negation of conditional is, I think, yeah, the negation of the whole conditional is the hypothesis and not the conclusion. So we can just Put that in there. And we're just gonna have a bunch of ands, right? So. This actually seems easier to read. The negation of the negation, we can apply double negation law, and this is just the statement. Okay. So what does this say? It, like I said, it better be true on students at UHD because he made this. Right? Oh, wait a minute, I got caught up on something. Sorry about that, I just saw it. Just because you made this false, right? It's like, it's you're this, or you're this, or.
Just because his was false, doesn't mean someone else.
It means the whole thing is true. Because y'all have false hypothesis, which makes it true. So this whole thing is true. Okay, you made it to, you're like one case where it's false, right? But there's at least one case where it's true, and it's the or, right? And y'all make this vacuously true because some of you don't have more than one friend at UHD, right? Okay. So if that's true, then this must be false. So for every student at UHD, there are two friends of that student that are friends.
That's not true.
No.
No, that's. But think about it, like, for every single student, for every single student at UHD, like, no matter what student I pick in here, I pick you, you have two friends that are also friends
Yeah.
that are at UHD.
Absolutely.
So that is definitely false. And look what just happened. This is like a really important point. Which one was easier to figure out what was going on? That or that?
Yeah, the first. I understand.
Like, let me like, if we, like, we had to like break down this, right? But like, the conditional was kind of throwing off and the negation was throwing off.
Yeah.
And I felt it. But over here, it's just like, right?
Wouldn't it still be true at some point?
No, for every, no matter if I pick,
Oh.
yeah, so
And the statement.
for any, yes, the and, it's like makes it, for me, it makes it easier to translate. So any student at UHD I pick, you have two friends that go to the school that are also friends. That's false. You're a counterexample because this is for every student, right? And we just need to provide one case where it's false in order for this to be false. Because the for all is like for you and for you and for you and for you and like every single student, this has to be true. Right? Whereas like here, we just have to find one example where it's true, which is I can pick most of you in here, and this hypothesis is never satisfied, and the whole thing is true. So this is why I asked to negate that original that we were looking at, right? The one before this. Because trust me, if you're looking at a statement and you're trying to determine the truth value, sometimes it's easier to look at the negation. Okay. And when we get to proving things, which I went over time, I was gonna try to squeeze in a little bit of proving things. When we prove things, looking at the opposite and showing the opposite this is a perfect way of establishing that this is true. We consider the opposite and see that it's false, which means the original statement must be true. And the original statement was in the form of if this, then that. A lot of mathematical statements are, if hypothesis is satisfied, then conclusion, or hypothesis, then conclusion, right? Yeah, you can prove, well, no, you prove that the opposite is a contradiction, always false.
Proof by contradiction.
Yeah, which means the original statement is true. Okay. I'm glad I did this example, because this was a fun one. So I think that's it. Yeah. So this was section from Rosen. .5 from Rosen. So I would read. Right, and that'll be it. All right, Tyler and Matthew, I will see y'all next time.